Okay, so hi everyone. Welcome to the last in-person session of QIP of this year. It is my pleasure now to introduce Jonas Haferkamp, who is going to talk about the linear growth of quantum circuit complexity. So please, Jonas.
All right, thank you very much. I'm going to talk about the growth rate of quantum circuit complexity in random quantum circuits. This is joint work with this wonderful group of people. There's Philippe, Faist, Naga, Kothakonda, Jens Eisert, and Nicole Halpern, who all contributed to this. So in the next 20 minutes, I'm not going to give you much of the proof details, but instead I want to show you some of the intuition behind basically all circuit lower bounds for random quantum circuits and explain to you how very different approaches have all the same underlying ideas. All right. Obviously, the key concept of this talk is quantum circuit complexity. And for many quantum info audiences, you almost don't have to introduce it because it's such a widely used sort of ubiquitous concept in quantum information. It's not very surprising, given that it essentially just quantifies how much resources do you need to, for example, prepare a state or implement an operation. And if you're practically or theoretically interested in protocols, quantum information protocols, obviously you want to know how many resources these protocols take. So the classical analog has been around for a very long time and is sort of pervasive in classical computer science, where it is related to all sorts of subjects, such as the separation of complexity classes, de-randomization, or communication complexity. The quantum version, even though also sort of a computer science definition, makes some surprise appearances in physics. So for example, the definition of a topological phase of matter uses the notion of circuit complexity. If you have a family of ground states of local Hamiltonians, you would say that these are topologically ordered if you cannot find a family of constant depth quantum circuits that generate these states. So in order to show that such a family is topologically ordered, you would have to find circuit lower bounds. A different, from my perspective, a little sci-fi application is in the context of the ADS-CFT correspondence, or more generally the holographic principle, where the circuit complexity is conjectured to correspond to the volume of certain wormholes. I'm going to talk more about this one because it is crucial for the motivation of the results on this talk. But before we do that, let's explain what I mean by circuit complexity exactly. So it is sort of a folklore result. You can find it in classical textbooks like Nielsen and Schwang, that every unitary and every state can be decomposed into two local gates, even exactly, using like it's gates like 4 to the n in the worst case. And obviously, from all these different decompositions, there's one that uses a minimal number of gates. And this minimal number of gates is what we call the circuit complexity of a unitary or a state. And let me just point out, I'm going to talk a lot about unitaries and at some points about states, but for every statement that I make about unitaries or states, there's an analogous statement for the other one. Everything can be just transferred. Obviously, what I mean by implementation sort of directly influences the notion of circuit complexity. So for example, if I allow an implementation error, then I usually, in general, need less gates to perform this task, to implement a unitary or a state. For us, however, the most important notion of complexity is going to be the exact circuit complexity, which is just the exact number of two local gates that you need to implement your unitary. So let's talk about holography for a second. The holographic principle, or more general, in particular, the ADS-CFT correspondence is this proposed dictionary between a bulk gravity theory and a boundary quantum theory. And in this dictionary, Susskind and collaborators sort of identified an apparent paradox. Because on the gravity side, the volume of certain wormholes seems to grow steadily for an exponentially long time. But if we map this to the quantum theory side, and this would correspond to a local observable, then this would defy our intuition about local observables in quantum theory, because we would think that this thermalizes very quickly, so the expectation value should saturate actually after a very short time. And the resolution that they proposed for this apparent paradox is that the dual to the volume in the gravity theory cannot be a local observable, but has to be something more complicated. And what they propose is the complexity, the circuit complexity of the state. Now, Whether this is true or not doesn't have anything to do with this talk, actually, but it implies something directly for complexity, which is, if this is true, then obviously complexity has to behave like the volume in these wormholes, and this leads to a sort of natural conjecture about this behavior, which is due to Adam Brown and Lenny Susskind. So the conjecture is that for an exponentially long time, the complexity grows steadily at a linear rate, such as the volume of these wormholes, and then saturates. And the important part about the conjecture is for an exponentially long time, because we sort of know that this is true for a very early time. Basically, we know that time evolution generates entanglement, and to generate enough entanglement, we need circuits of a certain depth, and this immediately establishes circuit lower bounds. The problem is that typical notions, like measures of entanglement, like the entanglement entropy, they tend to saturate after a polynomial time or polynomial depth in quantum circuits. The way I like to think about quantum circuit complexity, for example, is as a fine-tuned measure of entanglement, because it essentially measures the amount of resources that you need to rotate your state or your unitary back to a product. And in this picture, we can say it's very difficult to then disentangle a unitary. In fact, if I just give you a unitary now, I bet you money that you won't be able to tell me its circuit complexity. It turns out there's not a single family of unitaries that can be efficiently described for which an unconditional superpolynomial circuit lower bound exists. This is very similar to the situation in classical computer science, where you basically have no good family of Boolean circuits for which you can prove superpolynomial circuit lower bounds. And the problem is, while we believe that sort of accidental shortcuts, like a very small circuit that accidentally prepares the same state or unitary, are rare, they almost have no structure that we can exploit in proofs, in rigorous proofs. So it will be very difficult to rule them out for a specific unitary. But how do we make progress then on this conjecture? Well, one direction that we're not going to follow here is to prove superpolynomial complexity bounds from complexity theoretical assumptions. This is done by Aronson and Susskind and by Brandao-Bodanovic, who actually find particular Hamiltonians and then say if a certain conjecture in computational complexity is true, then for very late times, these need to have superpolynomial circuit complexity, these time evolutions. Here we want to focus on unconditional results. And the only way forward here, I learned about this from this beautiful paper by Brandao, Chemisani, Hunter-Jones, Killian Preskel, is to consider random quantum circuits, which are sort of a toy model for chaotic behavior, for chaotically behaving Hamiltonians. Why do I say toy model? It sort of looks like a trotterization, right, where we measure time as the number of layers. The problem is that it's time dependent, and we draw each gate IID at random from the Haar measure of the local unitary group. And Haar measure is just a fancy word for uniform measure on this unitary group. So why does this help? It turns out that these random circuits, because we keep adding randomness, generate very random ensembles of unitaries or states, and therefore we can make counting arguments work that work for the entire unitary group to some degree. For the entire unitary group, there's a very simple argument that shows most unitaries are in fact very complex. So for example, locally the Haar measure essentially can be mapped to a Lebesgue measure. So the volume of a small ball should scale like 1 over epsilon it should scale like epsilon to the dimension. But the dimension is 4 to the n, so this is doubly exponentially small. And just comparing this to the number of unitaries that you can generate with R gates from a fixed gate set, we see that to even cover a constant fraction of all the unitaries with respect to the Haar measure, we need exponentially deep circuits, actually scaling like 4 to the n. The idea is now that this can be de-randomized. Unitary t-designs are not the topic of this talk, but they are sort of pseudo-random distributions that cannot be distinguished from the Haar measure using only polynomials of degree t. So if your friend has like a distribution at home and you can only ever send them polynomials of degree t and they send you back the expectation value, you could never tell the difference. And it turns out that using this property, you can show that, for example, the overlap of having a state, the overlap with some state with low circuit complexity being large is exponentially small if you choose t high enough. And this can then be combined with sort of seminal results on the generation of these pseudo-random distributions by Brandao, Harrow, and Horodetsky, and can be turned into a sublinear lower bound on the circuit complexity, which also holds for exponentially long times. So I think this can be improved a little. There might be some follow-up work that I'm going to talk about at the next QIP, obviously. But unfortunately, I think just using the same proof techniques, it cannot be extended beyond a certain point. I think like t to the 5 is where we need completely new ideas. This might look like this. It's also not linear, but it works for essentially any notion of circuit complexity that you can come up with. So the new thing that we do now is we restrict ourselves to the exact circuit complexity and observe this is not only subject to volume counting arguments, but even a dimension counting argument suffices. So for the entire unitary group, just observe that the dimension of the unitary group is gigantic. And then if we consider the set of all unitaries that can be generated by 2 local gates, and by the way, I don't care about geometric locality, it can be like long range, doesn't matter. The only thing here that matters is that you have per gates about 15 different parameters, which is the dimension of the special unitary group on 2 qubits. So this scales linearly, and we immediately see that we don't even have enough parameters to generate a set of positive measure. So these will be a set of probability 0. And the idea is now to make this rigorous, because these sets are not manifolds. So we need to find a good notion of dimension. And the second idea is to then partially de-randomize this argument again, and not compare the dimension of these sets of unitaries that can be generated by 2 local gates to the full unitary group, but compare them to the set of unitaries that can be generated by brickwork circuits. And now to make the same argument sort of work, we need the lower bound on this dimension. And we also need to show that actually the entire argument goes through and that we have everything with probability 0, because the measure on these sets is a little bit more complicated than the uniform measure on the full unitary group, because it's sort of a push forward measure. Like it's not directly defined on these sets, and we don't even know how these sets look like. Luckily, however, all maps are polynomials, and we can use sort of a combination of a toolkit from topology and semi-algebraic geometry to define such dimensions for these sets, and also to show something very neat. And using this, we can achieve something. And what we achieve is we take this sort of mythological creature that I certainly lack the Herculean strength to struggle with, and we substitute it by something extremely tame, namely this dimension. And this dimension is tame because we can map it to a combinatorial problem. And the combinatorial problem, I really enjoy it. It's like a game, right? You take a circuit architecture. In our case, it's the brickwork architecture, but like think of any architecture of arranging the gates. Now fix your gates. And you are allowed now to insert Pauli operators after the gates, 2 local Pauli operators. And this is going to be a set of matrices. And I want to know the dimension of the span of these matrices. And if you maximize this over all choices of gates, this gives you the dimension of the set of unitaries that are generated by brickwork circuits of a certain depth. And the good thing is we only need a lower bound, right? And that means finding any example that generates enough linearly independent matrices like this immediately gives us a lower bound on this dimension. And for anyone who's like interested in the technical details, these appear as partial derivatives of the contraction map. So if you parameterize the map that contracts the circuit and you take partial derivatives along like Pauli directions, then these are the partial derivatives. And what we here see is basically the rank of the Jacobian of this contraction map in local points. So our example is very simple, and I'm pretty sure there's room for improvement on these bounds. But what we do is we simply say, well, okay, let's restrict to Clifford unitaries because that's much easier. And Clifford unitaries, they are defined such that if you take a Pauli operator and commute them through the circuit to the right, on the right-hand side, you end up with another Pauli operator. In general, this is going to be some Hermitian matrix, but in our case, it's a Pauli operator. And what we then do is we sort of make an inductive argument work. We say, let's say we have a circuit of a certain depth, and we have already created T prime many different Pauli operators like this. And of course, Pauli operators, they are orthogonal with respect to the Hilbert-Schmidt product. So if you have T prime Pauli operators, they generate a T prime dimensional space, or at least a T prime dimensional space. And let's assume we have now these T prime different Pauli operators, and now we pick some Pauli operator that is not in this set. And what we do then is, in our case, this is going to be the brickwork circuit, but it works more generally. We show that you can always pick these Clifford gates such that by commuting the Pauli operator through the circuit, afterwards you end up with a single qubit Pauli operator. This can always be done. And the idea is actually very simple. It's like you start wherever you have a non-trivial Pauli operator and you map it along some path to an identity tensor Z. And then you just follow this path and sort of remove the non-trivial Pauli operators until you finally end up with a single qubit Pauli operator. And the only thing that you need for this is like sufficiently deep circuits of linear depth. So now this single qubit Pauli operator is a Pauli operator that we have inserted after a gate in the circuit, right? So it is one of the linearly independent matrices that generate this image of the Jacobian. But we also know that this Pauli operator, simply by the way we chose it, is orthogonal to all the previous Pauli operators. So our lower bound just jumped from T prime to T prime plus 1. And we can make this work until we finally hit the full dimension of the unitary group. And this establishes, basically combined with this semi-algebraic geometry toolset, it establishes the following theorem, which is really the Brown-Susskind conjecture for random quantum circuits for the exact circuit complexity. We can show that we have a linear lower bound up to constants for computer scientists, because the scales that we care about is exponentially large number of gates. So these n squared or minus n over 3, for our sake, these are logarithms. And if you have sort of a computer science mindset, you don't care so much about them. That's what I tell myself. With unit probability, this holds, meaning with probability 1. And it actually doesn't just hold for exponentially long times, but for a maximal time, like until we hit the dimension of the unitary group. So this really finally establishes this linear growth. And also we can show that once you've hit this, this dimension threshold, it saturates and you keep, you have a exponentially complex unitaries forever, except with probability 0. With probability 0, you can have recurrences. Of course, like if you allow some error, then you have recurrences with a higher probability at some point. Let me just point out some future research. So first, I think for polynomial depth quantum circuits, something much stronger holds true. I'm actually almost certain that our lower bound on these dimensions is very loose, and I'm pretty sure that, so for linear depth circuits, for example, we can already show that they are perfectly incompressible, meaning most linear depth brickwork quantum circuits are their own minimal circuit description. And I'm pretty sure that you can push that for very high degree polynomials in the depth, or maybe even for all polynomials. That would be cool to see. Then also I'm very interested in notions of circuit complexity from a mixed state, and sort of related also monitored quantum circuits and how complexity behaves in them. There are some phase transitions for the entanglement properties for monitored quantum circuits, and I would like to see if complexity also shows some phase transition-y behaviors. And last but not least, the big one is obviously showing this for a robust notion of circuit complexity, right? Because the notion of circuit complexity that I've showed you is very restricted. And in fact, we can make tiny progress towards this goal. It's a little underwhelming though. I mean, we can show that there's some epsilon error larger 0 for which linear growth holds until exponentially long times. The problem is we don't know how this epsilon scales in the system size. So it could be like inverse Ackermann function, or like think of your favorite worst case scaling. Let me just point out, like, there are sort of very different approaches for this problem, and all of them fail for very different reasons. So for example, the unitary T-design thing is very robust, but it like fails because we can't make it linear. And I've spent considerable amounts of time on this problem, and I think by now it fights back hard the closer you get to it. And so it's either not true, or like I think it would be a very profound statement to show this. Last but not least, there are postdoc positions in Berlin. If you like these sort of questions, then talk to Jens. And I think I'll stop here and answer questions if there are any.
Hey, Jonas, thank you very much for this very nice talk. So if there are any questions, please just come to the microphone.
Yes, very beautiful talk. So I wonder, you prove or these results have any implication for coherent dynamics. For example, I gave you a family of local Hamiltonian stuff, and then you can generate a bunch of unitaries. So what's the
right? So basically, we could induce some randomness by simply considering an ensemble of Hamiltonians and then consider the time evolution of these. That might get rid, or you could think that this gets rid of this problem of ruling out shortcuts because you don't have structure to exploit. The problem is sort of, it's very little randomness. So all these techniques will never work because you have randomness once and you have like polynomially many random bits. And beyond that, you don't get very random ensembles that are so uniform that you need a lot of unitaries to generate this ensemble. Because what we have so far are brutal counting arguments, right? We just say these ensembles are so random that you need too many unitaries to generate them, and you simply don't have enough circuits of low complexity. And this can never work for taking a random ensemble of Hamiltonians and then consider time evolution, except if you consider non-local ensembles of Hamiltonians, but then maybe the notion of Hamiltonian is not so natural.
Okay, yeah, thank you.
Hi, very nice talk. I have one question. Welcome. I was wondering how essential this brickwork circuit assumption is to your whole derivation.
Not at all. I only used it as an example for the talk, but it works for any architecture that has what we call complete backward light cones. So if you sort of can find a path through the circuit to every qubit from some qubit, and then basically the scaling of the bounds is like 1 over the number of gates that you need to construct this backward light cones in your architecture.
So how about, for example, if you had something like SYK-like, you had some k-local circuits that can act non-locally?
Oh yeah, I mean, the higher the locality, the better.
Okay.
The better the bounds.
Okay, excellent.
Okay, thank you very much. Then let's thank the speaker again.